Hello, this is the summary of my 4th week of dev streams. This time I'm recording the intro when I should record it. That is on a Monday. I finished the stream just 20 minutes ago. Hopefully I will maintain proper efficiency for this week as well as productivity on streams because we'll talk how Monday turned out in a moment. Before we head on to the summary, a quick reminder that my Twitch channel is in the description and that I stream on every Monday, Wednesday, and Friday at 15 of Central European time, as well as on Saturdays later at 19 or 20. Any exceptions to that are informed on my Discord server, which is also in description. Before Monday, I've done no changes. Sort of quick changes I was supposed to do quickly. I tried to fix some of the bugs in the junkie pickup mechanism I've made on Friday, but after 30 minutes of doing weird things and failing ultimately to do anything about that, I decided I'll just go to work and not waste my time on this. So today's goal wasn't so obvious at the beginning, what should I do, because I had no idea what I wanted to do. So I quickly strategized and came up with a bunch of ideas. One was to code a query system which could be used for stuff like not making pickups and interactions in general overlapping in strange ways. You know, in most sensible games, is spatially what are you pointing at? The second idea was to integrate Fmod and work on a properly working audio system. That means I would be working on what I coded months earlier before I even began those dev streams. But reworking that I left to do in some private time. The third idea was to spend the day lazily modeling things, like modeling new weapons, some scene objects that could be lying around and maybe some interactions could be done with them, or entire levels, since blocking out the entire level using Unity objects kind of sucks. I decided on none of these. Instead, I decided on making a level zone system, which could be used primarily for loading and unloading rooms, and this way saving up things and in general optimizing the game, as well as some additional features that could be added in the future, like parametrizing audio or implementing deltas, that is, the displacements of objects that were from their original placement, or other optimizations that could be potentially related to that. And so that sounded like a quite simple project to work on for one stream, and so I got to work. So first, just to get some footing in the idea, I began to work on the zones and the potential query system for checking which zones are in which simulation range. I decided for a zone to be simply a mono-behavior class, whose main characteristic would be that it would have some bounds that would be calculated based on what children objects are assigned below it. In the end, it turned out that these bounds weren't useful for anything, but anyway, I spent a good deal of time thinking how to make the query system efficient and in-engine, and I relied on the idea of some physics checks like sphere cast or overlap sphere. These naturally require to use colliders, which I intended to implement already, since to check whether a player would enter such a zone, I would need a trigger collider. After that good deal of time, I however realized that there is a problem with this. Physics operations can be done only on enabled objects. And the main reason why we are even doing these zones is to be able to actually disable them. Realizing that, I went for a break to refresh my brain, and when I came back, I began to scribble a potential replacement architecture for the zone system that would instead check all these ranges manually. The result I got is something like this. The zones themselves would not communicate directly. Instead, they would communicate through a higher order object, a zone registry. A zone registry would also be a mono behavior. In fact, it would be a somewhat singleton object, except that it would not persist across scenes, and instead it would be glued to the scene it's in. So instead of one singleton per game, there would be one scene singleton per scene. The registry would have the information what zones are contained in the scene, and when called, it would handle the logic of adequately enabling and disabling the zones. Finally, the level manager, which I introduced on week 1 and didn't do anything about it since, would be the top orchestrator of the system. For now, it would just know about all active zone registries, and it might potentially do something about them in the future, but now it just knows things. Scribbling that, I also realized one thing. This system would allow me to play a bit with jobs and burst, special systems for efficient CPU-heavy tasks in Unity. And since I never had any practical experience with them, I realized that it would be a good moment to actually get familiar with them, especially that their application would fit nicely into the enabling logic. In the registry architecture, instead of doing some engine checks to query things the way we want, we could instead query all the zones in the scene mathematically and check whether their positions are in the simulation range of a given zone. And using jobs for that would actually help scaling up things really nicely, especially that later I've done some strange overhead. So having that, I proceeded to implement the system. I first created a class for scene singletons in general, like the zone registry, so that I could use them for some other things eventually in the future. And with that, I began to work on the actual registry. I first introduced all the basic methods like awake, on destroy, registration methods, as well as, of course, the list of the zones. I then began to actually implement the query logic, learning at the same time how practically jobs work. Actually, let's take some time to explain how jobs work because it's a nice topic. In abstract terms, a job is a way to somewhat parallelize your code in Unity. It turns out that Unity runs on multiple threads, for our interest specifically the main thread in which all the main logic is processed, as well as additional worker threads on which we can pass the code we'd like to execute aside from the main thread, in a fashion similar to shaders except on the CPU instead of GPU. Now, practically, a job is a struct object. A struct, not a class, since structs are allocated on the stack, which is much faster for computation than the heap on which classes are allocated. And partially, this is the reason for the speed of the job system. Now, the struct inherits from a special interface, iJob for a single worker thread operation, or as in our case, iJob parallel for that works on multiple workers. This is the one that is more similar to the shaders. Technically, inheriting this does two things. First, it requires us to define a method void execute, which takes an integer index as input, and this is the place where we actually perform all the calculations we want, and the index is kind of like the coordinates in the shaders. The second thing is that it allows us to actually use the job as a kind of coroutine or async task or whatever analogy you might bring to this. Also, the struct, apart from the interface and the method, needs to have some data to actually perform the calculations on, preferably fast in use and 100% heap free. The typical value types like floats, ints, and booleans work perfectly fine, but for other things like vectors, which you could use for example for positions, or arrays for storing all the possible objects, or in general custom C# object to use, we need some replacement for the typical work. Vectors can be supplemented from Unity's library Unity Mathematics, in which we have types like float3, which gives me some shader vibes again, which are better suited for this kind of work than the usual vector freeze. For the arrays, which in C# are actually reference types stored on the heap, are supplemented by special native arrays, which are structs using native memory. This, on the other hand, gives some C++ vibes, since the usage of those requires us to actually manually dispose of the array, since it's not collected by the garbage collector. It somewhat looks like declaring a pointer in C++, assigning a new instance object to it, then deleting it when we're done, otherwise we have a memory leak. Finally, for custom objects, like zones in our case, we create structs that contain all the information we need for the computation. In our case, a zone data contains a float-free position, a simulation range, the active state of the zones to be updated, as well as a guarding flag isColor set to true only for the calling zone to skip its own calculation, so that we don't disable it accidentally. Now with this, the job is basically ready to use, But to maximally speed it up, you can use the burst compiler, which is actually pretty simple to use. You simply slap a burst compile attribute next to it and you're done. Now, once you have the job declared, you need to somewhat use it. Actually use it in whatever method you want to use it in. You do the following things. First, you create all the data you need. In our case, it's the native array of all zones, as well as an individual zone data for the color zone. Then you create the instance of the job, typically using a var for that to let C# safely figure the types out. And to run this job, you create a job handle, which you set to the schedule method, which actually runs the thing. In the schedule method, you need to pass the length of your dataset, as well as the batch count for Unity's inner loop. This can be adjusted depending on how much stuff you need to do. Then, if you wanted to perform a different job after the first one, you would simply instantiate the second job and then reuse the previous job handle. Then finally, when you're done calculating all the things, you release the handle via complete, and then you can use all the data that was calculated in your job to do whatever you want. And when you're done with that, call this both on whatever native arrays you used so that you don't get a memory leak. Right, so after I finished coding the jobs, I needed to overcome a certain design challenge, which I kind of failed. This is how to properly trigger loading and unloading when you're transitioning between zones. Because you see, when you enter a zone, you should call the registry to load more zones in its simulation range. When you exit a zone, you should call to unload the ones no longer in the simulation range. The way I did it was to simply set everything in the vicinity of the zone to whatever state we want, so that it's the laziest system possible, and that causes a problem. Because when you exit a zone, it unloads everything around, including the zone you've just entered, as well as its loaded neighbors. To solve this problem, I came up with an idea to simply on exit call the registry twice, once to unload around the old zone and load the new zone. This idea, now that I'm editing, sounds a bit janky, and in fact it is, but I didn't come up with anything else on Monday. Now, to implement this idea, I had a bit of a struggle with how to actually do it, and after completely not thinking for a bit of time, I went for a break to refresh my brain again, and I returned with an idea to solve my problem. See, my problem was that first I got a bit lost on what references what and what passes what information where, including how to tell the registry what is the new or old zone. The idea was to update a class I didn't mention earlier, Simulatable, which up to this moment was simply a flag class assigned to object to filter them out when entering a zone trigger, so that only those objects actually trigger the loading and unloading, and not, for example, a barrel that would be thrown between zones. The update was to simply have a zone field in this class, which would be updated every time we enter a zone. Using this information when exiting a zone, the old zone knows what is the new zone, and we can pass this information to the registry. After implementing that, time came for testing the zones. After a bit of assignment hassle, I verified it works improperly. As I mentioned, my solution to the transition problem was a bit janky, and so I left this to solve the problem another day. And so, with that, I ended the Monday stream. Now, my complaint from the intro is that for the entire 4-hour stream, I was doing stuff which I would easily do in 2 hours if I wasn't so sluggish with everything. I complain about this since, paradoxically, I don't like wasting time, and yet I do it constantly. Wednesday was a strange day. It was kind of like a tiring multiplayer match. It was long, doing practically nothing for the first half, and then came a slight comeback, and I began to actually do things. So, for the quick fixes, like on Monday, I've done one thing for a bit of time, but this time I actually did something. Specifically, I fixed the issue I left on Monday, that is, fixing the loading. I've done that by changing the idea slightly, That is, instead of lazily unloading stuff around the old zone and loading the new zone again, instead I changed it to just unload everything beyond the simulation range of the new zone. That is obviously much better, and we performed the job once instead of twice. So, for the main work, I actually had an idea to work on, and it was to create a query system, which was one of the ideas I thought about on Monday. And this system would be simply querying some space in a cone in front of the player to check what things we could target, interact with, and find out what you are pointing the most at. To do it, I spent the first 1.5 hours trying to piece together how to actually make one that would fit, relying mostly on ChatGPT as well as my own stubbornness. Chat was giving some good ideas, except most of them weren't just for my project or preferences, or with some typical problems as typically AI generates. It's worth noting that AI obviously isn't the best idea to rely on entirely, and you absolutely should think for yourself and verify those things. But AI may be very helpful to figure out what you're actually doing. It's better to, spend 30 minutes with AI, watching through some of its junky concepts to realize what you actually want. In fact, this entire project, as I said way earlier in the previous summaries, is focused more on doing stuff myself and using AI as mostly a guide. Alright, so when I finally got some foundation to work on, I proceeded to work quite sluggishly on the elements of the system. I feel we don't need to describe the process chronologically since it was quite chaotic, and so we'll talk how the system turned out to work. So the query system relies on two independent parts, the query and the sensor. The query is technically a static class with a method to find the thing we are most pointing at, given some information, primarily the set of objects to query, and then the context and calculations. The sensor, meanwhile, is a mono behavior which checks what targetable objects are in the space around it, and the final version I decided on is by making it a trigger collider in the shape of a big sphere. This checks all objects that enter and exit the trigger zone, and checks if they are targetable. If so, it updates the set of objects inside, which we can use for the query. As for the smaller blocks that contribute to the system, we have the targetable class, a mono behavior we can stick to objects we want to target and query, which besides being a flag, contains some additional information, mainly virtual methods that could be overridden to alter the way they are queried, like adding additional scores or alternating the ways they are accepted and so on. We also have a context object, which, unlike the state context we used previously, is a struct, and it simply contains the basic data of our point of view: the position, the direction we're facing, the max distance, the cone angle, as well as a layer mask for skipping unnecessary objects. Speaking of structs, we also have a targetable data struct, which was made last minute to be used as an intermediate point between the referential targetable and the value only jobs. Finally, we have two interfaces, iTargetFilter and iTargetScorer, which allow us to modify the way we query the objects. Each contains a main method returning a boolean and a float respectively, each taking in a target context as well as a targetable data, or simply targetable before updating the system last minute to use jobs, which they use to calculate how to filter the objects and how to score them. The idea is that for the query, you can pass a list of various filters and scorers you might define, and each object is checked whether it can be considered by the filters, and then it has a calculated score by the scorers. The object with the biggest score wins. Also, a fun detail, if an object would have scored a negative number by one of the scorers, it would have its score set to negative infinity to maximally deprioritize the object. With careful scorer definitions, this can be used as a kind of gating. If there is anything even just barely positive, it will be chosen over a basically discarded object, which will be chosen only if there was no better alternative. So it doesn't quite work like a filter, more like completely devaluating the object. Now, I mentioned that the system was changed to jobs last minute. Well, I planned to use jobs nonetheless, But for easier workflow, I didn't integrate them for most of the stream, just barely converting most of the system at the end. Friday was a lot like Wednesday. First, I was fixing the previous system for 40 minutes, then talking to ChatGPT for again 1.5 hours to prototype the architecture for a new system, and then sluggishly implementing the system for the remaining half of the stream, of course, leaving it unfinished. So for the quick fixes, as well as the in-between stream changes, which kind of overlap in this case, is that I jobified the query system properly, which required some slight restructuring. Specifically, the issue was to preserve the freedom of assigning filters and scorers while being able to pass them to jobs which don't support polymorphism. The solution was to create some slight programmistic paperwork, that is, creating factories, classes that would take an arbitrary filter or scorer and fit it into a filter variant or scorer variant struct. A kind of rigid structure that contains all the existing filters or scorers and appropriately picks out their solutions based on an assigned enum. These are basically just collections of all existing filters and scorers. Then, with those variants ready, we pass them into the factory again to bind those into a native array usable for jobs. This forces us to do some more work when creating a new filter or scorer, since if we want one to actually work in the system, we need to not only define it, but also create a label for it in the enum, assign it in the variant struct, and add a check for it in the factory class. So it's a bit of more bookkeeping headache in exchange for a flexible and efficient system. So for the actual work today, I initially wanted to debug the query system to see some more details about its functioning, but that required some visual adaptation. After thinking quite a bit about making some dummy visuals, I realized that it would be better to just work instead on a full-on visual system, so that ultimately became the project for today. Problem was, unlike with systems like zones or queries, I didn't even wet my toes in the idea of how do you display a kind of inward UI in Unity, and I needed to learn how it should be done. So after asking ChatGPT how, supposedly, this is done in the industry, I learned that you typically do that by having either a UGUI canvas, mostly preferred even though it's the per UGUI, or a strange kind of UI document in the world. I chose the first one because the system was more about instantiating and managing objects rather than some abstract visual elements, and because I have a burning, passionate hatred for the UI toolkit system, which I also expressed on the stream when it took me 30 goddamn minutes to try to make a nicely working centered dummy crosshair and ultimately surrender doing a lazier version. So this canvas would have all the display widgets under its visual control, and the creation, management, and recycling of the widgets would be managed by a new singleton, World UI Manager. The widgets themselves are based on a presenter class, which is an abstract mono behavior that gives shape to the behavior of the widget, and from it we create subclasses for each kind of presenter, since an icon behaves quite differently from a tooltip or a health bar. Also, since we're talking about making unpredictable amounts of widgets at runtime, we also need some pooling system. For this situation, a very simple bare bones one, which we would use as an interface for the World UI Manager, which would ask the pool to handle the given widget instead of taking care of it itself. Finally, to have a source for the widgets, have providers, model behavior classes inheriting from a special iWorld UI provider interface. We could assign those to the targetable objects and somewhat integrate the widget system into the query system. The process was chaotic, boring, and unsure since I was barely doing stuff myself and I was trying to carefully analyze what ChatGPT spat out. At the end of the stream, the system was completely not debugged, barely set up, and so I'll need to do some more cooking with it later. So the pattern repeats. Friday is the worst day of each week, it seems. And so that was week 4. In terms of reflections, I should slow down a little and rethink some things to not have constantly systems collapsing on every next day to fix them. Because right now I'm kind of lacking an overarching view of what I'm actually doing. The goal is to have a sound design sandbox, but you see how it is, how it evolves. At least I got somewhat into a more efficient scheme of streaming and editing, though I still got into procrastination and turned out that I'm recording this ending on Monday before the stream. In fact, I delayed the stream today because the exporting will take some time. Yeah, will not further delay that. See ya next time.